WebSockets equal TCP with a long-lived upgraded connection. Even though WebSockets look like a different protocol, they run 100% on top of TCP. Step by step. First, browser sends HTTP request to server get/chat http/1.1 upgrade WebSocket connection upgrade. Second, server replies http/1.1 101 switching protocols next line upgrade WebSocket. Third, that same TCP connection stays open, no more HTTP. Fourth, client plus server send frames in both directions anytime. No more request response, no more polling, no opening or closing sockets thousands of times. So you don't need to open sockets or buffer to the OS once you made your initial WebSocket request, because that same TCP connection stays open and no more HTTP. That's the advantage of WebSocket. And then after that, the client plus server send frames in both directions anytime. How real chat apps implement this in real world? Here is how big apps run their real-time messaging today. Meta Messenger, real-world architecture. Messenger historically used MQTT over TLS over TCP, not WebSockets. MQTT equal lightweight, persistent TCP pub/sub protocol. Messenger's flow, client to long-live TCP or MQTT connection to Edge, Envoy, to chat service, to Kafka, to fanout, to InboxDB. So as you can see, from client, it send it to TCP or MQTT connection. Then Edge, which is their kind of like CloudFront, and then the actual chat service, and then Kafka. So they also use Kafka just like with Twitter timeline service, then fanout, then InboxDB. Why MQTT instead of WebSockets? More battery efficient, smaller frames, works better on mobile, handles disconnects well. So Facebook actually does not use WebSocket because there is a framework that allows that is better on mobile and handles disconnect well, that also have smaller frames and battery and is battery efficient. This means Messenger is still TCP based just like WebSockets, same underlying transport. WhatsApp uses custom protocol over TCP similar to Messenger, also maintains persistent TCP connection for incoming messages. Discord use WebSockets for real-time events plus UDP for voice, but the WS connection equal one long-lived TCP socket. Slack uses WebSockets via TLS/TCP for real-time messages, presence, typing indicators. So your statement is correct. Most chat apps still use TCP. They just use long-lived connections on top of it. It may not use WebSocket, but it still uses the same underlying principle behind WebSocket, which is a long-lived connections. How WebSockets and TCP connect to database architectural concepts. We bring everything together. A message sent in Messenger actually goes through this pipeline. A, client side, from user types to WebSocket or MQTT, then send over long-lived TCP. B, Edge, AWS ELB/Envoy receives the frame. So actually it's not the CloudFront, the Edge is actually an ALB that handles the packet, the firewall for that packet. Then C, the actual backend chat service, it checks auth if it's an login user, rate limiting if it is sending a lot of messages in per minute, or per seconds, spam, content policy. Sometimes this backend chat service also check for the insulting words. Letter D, publish to Kafka, fire hose of messages. This is the part connected to all our previous conversations. Why Kafka? Because it can handle millions of messages per second. Supports fan out to many consumers. Guarantees ordering with a partition. Though it may not be a fan out, right? Kafka support a fan out to many consumers, and it can handle millions per second. That's why this service has been chosen. Fan out workers, you ask, is this real? Do people actually do fan out workers? Yes, this is exactly what Meta, Twitter, TikTok, Discord do. Fan out workers read from Kafka, duplicate the message to each recipient's inbox, materialize timeline, write it to Redis or DynamoDB or RocksDB, also send push notifications. This is directly linked to your work at write versus read concept from Twitter's home timeline. So if you send message to a group, it will duplicate the message kind of like the same as a fan out, right, in Twitter. And then it will write it to Redis or DynamoDB or RocksDB and also send a push notification to them through their app. Exactly the same. Chat apps pre-compute inboxes, fast reads, low latency. So just like Twitter pre-compute the write to the followers, chat apps also pre-compute inboxes so that they have fast reads and low latency. Database connection. Messages land in DynamoDB or RocksDB or MySQL shards persistent history. Redis hot cache for extremely fast reads. So Redis is actually for cache if it is there before or something like temporal or spatial locality, it will take advantage of that. Elasticsearch, search for old messages. So this is also how you were able to search fast text or your old messages in Messenger. Read must be fast, consistent with tail latency discussion. So because this app needs to maintain that service or that fast lookup, they need to provide Elasticsearch tool for that. Tail latency plus fan out plus microservices connection. Remember, if one backend call is slow, your will request is slow. WebSockets help because no reconnecting means fewer slow path operations. HTTP or HTTPS creates new TCP handshakes, slow. WebSockets keep one connection open, predictable performance. So WebSocket no reconnecting while HTTP creates new TCP handshake each time they made a request. Quick reduces kind of like a server-side rendering of PHP. Quick reduces tail latency even more. Modern chat apps, Snapchat, TikTok, experiment with Quick for mobile because no head of line blocking, TCP problem. So Snapchat actually used Quick instead of TCP. So it used the UDP under hood unlike Facebook, so that they don't experience the head of line blocking of TCP, and it will have faster loss recovery. Uses connection IDs, not friendly. Less kernel involvement, fewer scheduling delays. So because Quick is in user space, you less likely need to interfere with the OS in your application code. So you less likely need to write kernel specific details but move that instead in the user space. Therefore, you also have that fewer scheduling delay. So instead of affecting the actual OS in your virtual machine, you're gonna have to work around in the user space. This connects directly to your question about how Quick reduces jitter, tail latency amplification, head of line blocking, not traversal, kernel socket buffer delays. How messaging apps avoid fan out amplification, real world techniques in AWS like architecture. First, minimize microservice fan out. Use single service that owns the inbox materialization. Second, pre-compute user inbox. Same idea as Twitter's home timeline. Write heavy architecture, cheap reads, no fan out on read, low, low tail latency. Third, put inboxes in Redis. Read latency becomes P50 colon 1 milliseconds. For P99, 2 to 3 milliseconds. P99.9 still predictable. Fourth, use CDNs for attachments. Images and video equal CloudFront. Removes tail latency from object storage. Fifth, HDR histogram monitoring. AWS X-Ray plus CloudWatch metrics support HDR histogram style calculations. This avoid tail latency spikes. How database architecture integrates with WebSockets real world. Here's a combined real world diagram. Client, WebSocket over TCP, to Edge, ELB to Envoy or Envoy, to Chat API service, to Kafka. So Kafka is where the write heavy work fan out. To fan out workers, to Redis, which is the hotchat inbox. This is where you do the cache, and to or along with this is DynamoDB, which shows the history of the chat. Then read API, which is fast. Then it will call client via WebSocket, receives updates instantly. That integrates TCP or WebSockets, Kafka, fan out, pre-computed inboxes, tail latency avoidance, Redis or DynamoDB. Database architecture, quick benefits, CDN for media. Everything you ask for is there. Summary, how messenger-like chat apps actually work. Transport, persistent TCP, MQTT or WebSocket, Backbone, Kafka, Flink, RocksDB, Redis. Database, DynamoDB, MySQL shards. Architecture, write heavy fan out, materialize inboxes. Tail latency reduction, no fan out on read, histograms, CDNs. Protocol evolution, quick replacing TCP for mobile reliability. First, okay, so for AWS, how does it actually work? How different real-world applications are being implemented in cloud with connection to the database concepts we discussed. First, AWS, Node.js Kinesis producer plus Node.js Lambda consumer that writes to DynamoDB. Second, Kafka, Redis worker, Go consumer plus Docker compose, Kafka, Zookeeper, Redis. Third, Prometheus plus HDR histogram instrumentation for the Go worker with a small /metrics exporter and example Grafana dashboard JSON panels for P50 P95 P99. Fourth, FFmpeg script to transcode input into multi-bitrate HLS and Dash production ready flags. First, AWS, Node.js Kinesis producer plus Lambda consumer to DynamoDB. Summary, so this is the real code that we would write to in creating Twitter fan out workers. So summary, producer slash is a local node script that put record to a Kinesis stream. Consumer slash is a Lambda handler node.js that processes Kinesis events and writes items into DynamoDB. Notes before running, create a Kinesis stream, i.e. my-stream, and a DynamoDB table, i.e. events table with ID as partition key. IAM roles, Lambda needs kinesis, get records if polar, but for event source mapping, kinesis to Lambda grant AWS Lambda kinesis execution role and DynamoDB put item to the Lambda role in your IAM role. Producer needs AWS credentials or run locally with AWS configure. This code uses AWS SDK v3 or version 3. So in this file, producer slash package.json, we have opening semi-curly bracket, key value name, kinesis producer, code, comma, code version, code 1.0.0.0, comma, next line, code main, code send.js, next line, code dependency, opening semi-curly bracket, next line, code at aws-sdk/client-kinesis, code 3.4.0.0. So this is the version, comma, next line, code UUID, code 9.0.0, closing semi-curly bracket, closing curly bracket. For file producer slash send.js, we have so this is for usage, AWS creds via env or shared config.node send.js. So we have import open semi-curly bracket kinesis client, comma, put records command, closing semi-curly bracket, from code at aws-sdk/client-kinesis, semicolon, next line, import open semi-curly bracket v4 as UUID v4, closing semi-curly bracket, from code UUID semicolon, next line, const stream underscore name equal process.env kinesis underscore stream, double vertical line, code my dash stream semicolon, next line, const region equal process.env aws underscore region, double vertical line, code us-east-1 semicolon, next line, const client equal new kinesis client, opening semi-curly bracket, region capital region, closing semi-curly bracket, closing semi. I don't think it's worth it to mention this, but we have an async functions and event payload here with the const data, const partition key, const cmd, const res, then return res, and we have async again, and then for let I equals, and then const event id UUID. We have key value user id user, key value ts date.now, key value type tweet, key value type body hello world, close semicolon, close semi-curly bracket, close semicolon, then next line, const r equals await send event argument event, next line, console.log argument code sent, comma, event.id, comma, r, close semicolon, then next line, await new promise, r to set timeout, argument r 200, then run cd producer npm, next line, npm install, next line, aws underscore profile equal your profile, then space aws underscore region equal us dash east dash 1, then space node space send.js. Then for file consumer slash package.json, opening semi-curly bracket, code name kinesis dash lambda consumer, then next line, just fast lock it, key value version 1.0, key value mean index.js, next line, key value dependencies opening semi-curly bracket, next line, code aws-sdk/client-dynamodb 3.4, then next slide, key value UUID code 9.0, closing semi-curly, then we have file consumer slash index.js. This is the lambda handler, so we import here DynamoDB client, comma, put item command, from aws-sdk/client-dynamodb. Next line import and Marshall from aws-sdk/util-dynamodb. Then next line const region equal process dot env dot aws underscore region double vertical line code us dash is dash one. Next line const table equal process dot env dot table underscore name double vertical line events table semicolon. The next line const db equal new data DynamoDB client open semi-curly region colon capital region. Then next line we have export const handler equal async argument event comma ctx rather parameter event comma ctx. The next line const puts equal empty array semicolon. Then for const rec of event dot records const payload equal buffer. Then let object try object const item key value id colon 5 user id colon 5 ts colon and payload colon etc. Closing semi-curly bracket semicolon. Then puts that push argument db that send argument new that put item command argument table name colon table comma item colon item. The next line then closing semi-curly bracket. Next line await promise that all parameter puts then return status code colon 200 comma process colon puts that length closing semi-curly bracket semicolon. So this is the lambda function. In deployment we have the zip consumer slash contents and deploy as lambda with node 18 runtime. Create an event source mapping from Kinesis stream to lambda batch size i.e. 100 comma window 1 second. Then set environment variable table underscore name equal events table for the lambda function. Then attach IAM policy allowing DynamoDB colon put items for events table. The next line second Kafka to Redis worker go plus Docker compose. Now goal run Kafka plus Zookeeper plus Redis in Docker dash compose comma produce sample message with Kafka console dash producer consume with a small go worker that zad into Redis sorted set i.e. timeline per user. So in docker dash compose.yml we have version colon 3.8 services colon indented zookeeper colon indented image colon confluent inc slash cp dash zookeeper colon 7.4.0. Next line environment colon next line indented zookeeper underscore client underscore port colon 2181. Next line zookeeper underscore tick underscore time colon 2000. Next line back indented ports colon 2181 colon 2181. Then for Kafka we had image Kafka colon next line indented image colon confluent inc slash cp dash Kafka colon 7.4.0. and the next line depends dash on colon argument parameter zookeeper. Next line environment colon next line indented key value Kafka broker id colon 1 key value Kafka zookeeper connect colon zookeeper colon 2181 key value Kafka listener colon plain text colon slash 0.0.0 colon 9092 which is the port. Next line Kafka advertised listener colon plain text colon slash Kafka colon 9092. Next line Kafka underscore offset underscore topic underscore application underscore factor colon 1. Next words back indented ports colon 9092. Next line Redis colon next line indented image colon Redis colon 7. Next line ports colon 6379 colon 6379. Next line Kafka worker colon next line indented build colon dot slash Kafka worker. Next line depends underscore on colon argue parameter open square bracket Kafka comma Redis close square bracket. Next line environment colon next line indented Kafka underscore brokers colon Kafka colon 9092. Next line Redis underscore addr colon Redis colon 6379. Next line command colon key value command colon Kafka worker. Then next is the Kafka worker slash Docker file, and we'll just continue with this in the future.